Thanks to CuriosityStream for sponsoring this video. Since well before the first Wright brothers' flight in 1903, and all the way to the present day, mankind has been fascinated by taking to the skies. Once thought to be impossible, heavier-than-air flight is only a reality because of the lift generated by aircraft wings. But lift is a complicated topic, and even to this day, engineers have lengthy debates about how it's created. So what exactly is lift? When fluid flows past an object, or an object like this plane wing moves through a stationary fluid, the fluid exerts a force on the object, which can be split into a component acting in the same direction as the fluid flow, called drag, and a component acting perpendicular to the flow direction, called lift. When talking about lift, we're mostly interested in streamlined bodies like this airfoil, which are carefully designed to produce a lot of lift, but to minimize drag. Lift-producing airfoils can obviously be found in airplane wings, but also in many other applications, like wind turbine blades or propeller blades. They're also used in the wings of Formula One cars, which are designed to generate downforce so that corners can be taken at higher speeds. Airfoils come in a huge range of shapes and sizes. One designed for an aircraft wing won't be optimized for a propeller blade, for example, and a wing designed to fly at supersonic speeds will have a very different profile compared to one designed to fly slower than the speed of sound. Airfoil profiles can be defined using a few different parameters. The forwardmost edge of the airfoil is called the leading edge, and the trailing edge is at the back of the airfoil. Drawing a straight line between the leading and trailing edges gives us the chord line. The angle between the chord line and the flow direction is called the angle of attack. Drawing a line which is midway between the upper and lower surfaces gives us the mean camber line. Camber describes how curved an airfoil is. We can have positive camber or negative camber, and a symmetrical airfoil has zero camber. Camber and the angle of attack are important parameters that will have a large influence on how much lift an airfoil can generate. So how does a humble teardrop shape generate enough force to lift heavy aircraft off the ground? As the fluid flows around the airfoil, it creates two different types of stress which act on its surface. First, we have the wall shear stresses. These stresses act tangential to the object's surface and are caused by the frictional forces that act on the airfoil because of the fluid's viscosity. Then we have